In the last class, we were basically wondering about the reflection coefficient, and we said that this gamma is some corresponding to some impedance Z is nothing but minus Z naught by Z plus Z naught. Further, we said that if Z is passive, then mod gamma is less than or equal to 1, and this simply follows from energy conservation. So basically, the incident power part of it is reflected, and the rest of it is dissipated in the impedance, and therefore, if you know that the impedance is passive, the power dissipated in it must at least be 0, and therefore mod gamma is less than or equal to 1. And another thing that I would like to point out is the following. So if you think of this the impedance normalized to the characteristic impedance as small z, then gamma, as you can see, is simply nothing but z minus 1, small z minus 1 by small z plus 1. And have you seen this before? This is a complex function, right? I mean, the small z is a complex number at a certain frequency, correct? And gamma is obviously also a function of a complex number, right? So this is gamma is a function of a complex variable, and so therefore this is an example of what you call a. Have you seen this before? This function z minus 1 by z plus 1 in some other context? Where? Yes, no, I mean, you either seen it or you have not seen it. Danish. Okay, well, this is an example of what is called a bilinear function, which is simply a complicated way of saying that the numerator and denominator are both first degree polynomials in small z. Now, if you have the z plane, right, where you have the real part of z on the x axis and the imaginary part of z on the y axis, for each point in the z plane, you can think of, this is the gamma plane, you basically will have a point in the gamma plane, yes, because you simply plug the small z into this formula and you will get another complex. Small z is a complex number, right? You compute small z minus 1 by small z plus 1, which happens to be the reflection coefficient in our case, right? You will get another complex number, right? So you can plot that complex number in the graph on the right, and that is the plane that shows that's also a complex plane, but it indicates, the x-axis indicates the real part of gamma, and the y-axis indicates the imaginary part of gamma, correct? So if you trace a curve here, what will happen on the in the gamma plane? You will have some other curve here, right? I mean, okay. But there is a special property of a bilinear function. I mean, of any transformation of the form az plus b divided by cz plus d, and it is what is called conformal mapping. I will explain what that means. But a couple of things that I'd like to first point out. The mapping 1 over z, right? This is the only thing you need to know. I mean, you can prove it easily, but I'm not going to spend time proving this here, right? If it turns out that if this 1 over z is, I mean, if you take a complex variable z and you compute a new variable 1 over z, then if z traces a circle, right, then it turns out that gamma will also 1 over z will also trace a circle. Okay. So, if z traces a circle, 1 over z will also be a circle, and you can calculate what the radius and all this stuff will be. So, the key point is to understand that if z is a complex number and if z goes around in a circle, then if you plot 1 over z, then that will also be a circle, correct? And remember that a straight line is simply a special case of a circle with an infinite radius. So, all that this means is that if z is a straight line or a circle, 1 over z will also be a straight line or a circle, right? I mean, a straight line in z can become a circle in 1 over z and vice versa. But the key point is to basically remember that 1 over z basically will simply be a circle if z is a circle. Okay. Now, this can be easily proven, and I leave it to you as an exercise, right? But this is one of those facts of life that is good to remember. Now, so if this reciprocal mapping is what do you call, that a straight line becomes a circle, and I mean, whatever, straight lines and circles remain straight lines, and whatever, when you find the reciprocal, it also becomes either a straight line or a circle. Then it's easy to see why this gamma, when you compute z minus 1 by z plus 1, which can be written as 2 minus, 1 minus 2 over z plus 1, correct? And so you can think of this as the following way. If let us say you had a circle in the z plane, right? Okay. How does z plus 1 look like? It's a circle which is shifted by 1 unit, correct? Okay. Then what are you doing? You are finding the reciprocal of that complex number, right? So, how will the reciprocal look like? It will also look like a circle, right? Then you are multiplying it by 2. So, what are you doing to that circle? Well, you are making the circle bigger, right? And then you are multiplying it by minus 1. What do you do? What does that happen? It's getting flipped from left to right, okay? Then you are adding 1 to it. So, what is happening? Shifting in the horizontal direction, right? So, bottom line is that if you had a circle to begin with, then doing this will also result in a circle. Okay, all right. So, that is the so if you have a circle here, you basically will it will turn out that you will be some circle like this. We do not know the details of the circle, but we know it is going to be a circle. All right. So, with this background, let us see what happens when we have a passive impedance. If if you have a passive impedance, where is the locus of all possible impedances? Pardon? In the z plane, where? Yeah. So basically, you're only in this area, right? In the RHP. Okay. The real part is positive. The imaginary part can be either positive or negative. Does it make sense? Right? Okay. Now let's. We know that if we now plot what happens with some crucial points on the z plane in the gamma plane, right? This is also called the reflection coefficient plane, right? So what comment can you make about the y-axis in the z plane, or the imaginary axis in the z plane, right? So basically that corresponds to z equal to some jx, and gamma therefore is nothing but jx minus 1 by jx plus 1, where x goes all the way from minus infinity to infinity. So how will this look like? Well, when x is 0, where are we? Oh, well, we are at minus 1. Okay. When x is infinity, plus infinity, where are we? So this is minus 1 plus jx by 1 plus jx. So as x becomes infinity, where are we? What is the angle of this guy? Is plus 90, and the bottom one is also plus 90. So basically it is at plus 1. That's here, right? Okay. When the jx is somewhere in the middle, let's say it's large and positive, how is it going from minus 1 to plus 1? You can see that the radius of this, for whatever value of x you have, the radius is always, what is the magnitude of this complex number? 1. So this is basically a circle with the radius of 1. Okay, not a particularly nice circle, but let me see if I can. Looks like there is no tool here which can draw a circle. Never mind. Okay. All right. So this corresponds to, and the origin basically corresponds to this point, corresponds to that point. All right. And that makes sense, right? Because if the impedance is a perfect shot, then the reflection coefficient is minus 1. All right. Now, if you have a line like this, what do you think will happen? This is 0. I mean, well, what curve inside the unit circle, inside the circle? It should touch, okay, as you go to plus infinity in this direction, what happens? In either direction, what should happen eventually? Plus or minus, if you go along this line where you have a positive real part and an imaginary part which goes to plus infinity or minus infinity, what would you expect to see for the reflection coefficient? What is, so in other words, you have R plus jx minus 1 by r plus jx plus 1. As x tends to infinity, what comment can you make? It will be 1, okay. When you have x is 0, what comment can you make? R minus 1 by r plus 1. So, where is that going to be? It will be on the real axis, right? Okay. So, depending on where you what you choose r to be. If r is exactly equal to 1, where will you be? You will be at the origin, right? So, this corresponds to r equal to 1, okay, and this part is for r less than 1, and this part corresponds to r greater than 1, correct. So, as you keep going, depending on the value of r, the starting point will change, but eventually they will all end up at 1 plus 1, right. So, and we know that all these must be, this is a straight line, and after transformation it must become either a straight line or a circle, right. So, this basically is clear that they must be circles which all meet at infinity. Okay, and all these are loci of where the resistance is constant, right. It is only the reactance varies. So, these are often what are called constant resistance circles. All right. The next thing is what comment can you make about this entire space? Therefore, we knew this already. Pardon? Yeah, I know what will happen. Where will that entire space map to in the gamma plane? Yeah, so basically it is inside the unit circle, right? Okay, and if you kind of mentally imagine, what you are doing is taking this long line and kind of pushing it to make it a circle. I mean, imagine you have you make a cut along here and then you kind of take that line and then make it a circle. Whatever is towards the right of the line will be inside the circle, right? Now, okay, what comment can we make about say this guy here now, where the resistance is varying, but the reactance is constant. So, now R varies from 0 and this keeps going to infinity. R varies from 0 all the way to positive infinity. So, when R is 0, where are we? We are here, correct, and therefore, on this picture where are we? Yeah, where? I mean, the unit circle is a big place, man. It's like saying you're somewhere on IIT campus. Yeah, so basically remember that what we have done is simply taken this vertical line and kind of squished it and made it a circle. So, whatever happens here will happen somewhere there on that axis. Exactly where depends on where exactly you are here, but this part corresponds to this part. Alright, it's a nonlinear mapping of course, right, but this part corresponds to this part and this part corresponds to that part. Is that clear, people? Okay. So, okay, that we know what happens there, and as r goes to infinity, where are we? See, whether x goes to infinity or r goes to infinity, it basically is like an open circuit where the reflection coefficient is +1. So, as r tends to infinity, you must go there, right? And how will it go there? It will go like a circle like this, okay, and I'll tell you why it goes like a circle like this. It turns out that a bilinear mapping, this is also what is called a conformal mapping. And any of you who's done complex analysis course probably has seen this before, right? And what it means is that if you have two curves and you have an angle between these two curves here, when you map these two curves using this bilinear mapping, then the angle between these two curves here will be preserved here, okay. And again, I mean, this is it's easily proven, right, and I encourage you to try it out. So, as you can see, therefore, I mean, the angle between the red line here and the blue line here is 90 degrees, and so at the point of intersection, you will find that these circles are basically those two at the point of intersection, the angle is still 90 degrees. So, you have now a family of for different values of reactance, you will have different parts of circles like this, okay. And remember, these 2 points in the z plane, where do they meet? Where do the two parallel straight lines meet, folks? Infinity, right? And so they meet at a point. The infinity in the z plane maps on to what do you call +1 in the gamma plane. So all these vertical lines and all the horizontal lines all meet at infinity. So they all basically meet at +1, right? The angle between the blue lines in the z plane, right, okay, is always, they meet, but when they meet, what is the angle between them? Angle between them is 0, correct. So basically they all kind of approach the +1 in that fashion, and when they meet at infinity, the red line is still perpendicular to the blue line, right. So you can see that when all the red lines, the red circles approach infinity +1 in this way, all the blue circles approach infinity in the horizontal direction, and the angle between them is still 90 degrees. So the red circles are all the so called constant resistance circles, and the blue lines, the blue circles are all constant reactance circles, and all right, okay. So and I mean this is of historical importance, and also I mean those of you who are using RF measurement equipment will also see this, or reading RF papers will see this often. This diagram, the reflection coefficient diagram, often plotted, and this is often called the Smith chart. All right, and the question is why should I bother about this, and why is this useful? Remember that if z is very large compared to 1, that the small z, which is the normalized impedance, which is the impedance normalized to the characteristic impedance Z0, if it deviates from z equal to 1 or z equal to Z0 by a lot. So this is, let's say this is let's say this is the line that corresponds to r equal to 1, okay. In here it will be this circle here. If you have an impedance and if it deviates a lot from this r equal to 1, right, I mean whether it is here or a large part of this paper is pretty much gives us almost no information as to, I mean the most of the power is reflected, correct, okay. So I mean what you can say, I suspect, I mean is basically that the farther you are from this r equal to 1, I mean the details of where exactly the impedance is hardly matter as far as the amount of power being reflected or absorbed are concerned, right. So one way of thinking about it is that, oh well, if you have a certain space to convey information, most of that space here is wasted because, well, all the action is around r equal to 1. If you want to, if you want, for instance, to design a load which basically absorbs all the power, I mean all the power that's delivered by, that's incident on it by a source, right, you eventually want to make sure that you do whatever it takes to get to this point r equal to 1, right, okay. And that was for example a very important thing in and still remains an important thing, right, and that is called impedance matching, where the idea is, as we have seen yesterday, you want to minimize the amount of power that is reflected by the load, right, you want it to absorb everything. For instance, you might be at the front end of an RF receiver and some RF power is coming in and you want to absorb as much of it as possible. That's one possibility. You might be an amplifier driving an antenna, and there it is imperative that whatever you put out is all transmitted by the antenna, is absorbed by the antenna, so that absorbed by the antenna means that it is transmitted out into space, right. There you want to make sure again that the amount of power reflected back from the load is as small as possible, right. And so in other words, you really care about the reflection coefficient being as close to 0 as possible, right. So in other words, you are particularly worried about impedances in that region there, right, okay, okay. And even say a small deviation from say r equal to 1 to say r equal to 2 already basically means that you are reflecting say 30% of your power back to the source, okay. So in other words, this is where all the action is happening, right. And if you think, if you have an amount of space to show an impedance, basically all the action is here, but most of the space is just simply getting wasted, showing parts of the z plane which we know are not really relevant. Okay. And if you want to calculate the reflection coefficient, every time you need to go and do the z minus 1 by z plus 1, alright. So, a more convenient thing where the where this area, right, is basically dedicated a lot more space, and the farther you move away from this this space, right, from that area, I mean, that that part is not really important, right. So, whether your impedance is here or here, it hardly matters, because the reflection coefficient is 1 in both cases, right. So, it's the reflection coefficient chart is a lot more useful in practice, and so in the early days when you didn't have calculators which would do the z minus 1 by z plus 1 with complex numbers quickly, right. If you had a chart which basically plotted the reflection coefficient plane rather than the impedance plane itself, then you would be able to kind of this area basically here, the critical area here basically translates to a large part of that picture. So, basically you dedicate a large portion of that area to, within quotes, the information bearing part of the z plane, right, and all the periphery is basically reserved for within quotes unimportant parts of the z plane, right. And you'd be able, and what is the so let us say you had some impedance, you can plot it once you know its resistance and reactance, you can plot it, you plot the point immediately. For example, right, let's say your resistance is less than 1 and basically your reactance is some positive thing. You can say, well, this is my impedance z, right, plotted in the reflection coefficient plane, and I can immediately read off the reflection coefficient. How will I be able to read off the reflection coefficient? This is the impedance, right. What is the reflection coefficient? How would I be able to find the reflection coefficient? I mean, this is the gamma plane, right. I have marked the point here. What is the magnitude of the reflection coefficient? It is simply the radius of this circle, right. The distance from the origin is simply the reflection coefficient, alright. Okay. So, what do you call, and then it turns out, for instance, if you had an impedance and here, for instance, okay, and so this is ZL, alright, and let us say I need to do something to make sure that this impedance is actually Z naught. So, I will try and put a network between my source and the load in an attempt to make the looking in impedance equal to Z naught, and this this network better be lossless, because I want whatever power is being drawn from the source to go eventually into the load. So, this is, you can think of it as a transformer which transforms ZL into Z naught, right. But this only works at one frequency, unlike the transformer that you are familiar with, which works at all frequencies, okay, alright. So, for instance, if you are here and you want to get to, I mean, if the looking in impedance has to be Z naught, you eventually have to get where on the Smith chart? You have to get to the origin, right. So, one way of thinking about it is basically that you can, well, you can travel, for instance, like this, right. If you want to get from that point to that point, what do you think I could do? Well, in principle you could add series resistance, but that basically defeats the purpose of the matching network, right. Okay. so what you would want to do actually, it turns out that you add I mean, once you plot the impedance chart, you can also kind of figure out what the constant admittance circles are, right. I think it's not particularly useful in this class, and therefore, and those of you who are interested can go and look up a Smith chart and how you can design matching networks which basically allow you to realize an input impedance of Z naught, okay, even when ZL is not what you want it to be, right. I mean, a trivial example would be, for example, if you were here, right. Okay, what do you think you could do to get to clearly the reactance, the resistance is 1, the reactance is not what you want it to be. So, what do you think you could do? You add the appropriate reactance to go from, you are on a constant resistance circle, and so basically you go like you add the appropriate reactance to cancel out the reactance that ZL has already, and you will end up with a matched input impedance, right. If you are not on a constant, I mean on the circle corresponding to R equal to 1, you can add appropriate elements in shunt and series to basically get onto this circle, and then eventually add a series element to get back to Z equal to 0. Sorry, gamma equal to 0. So, what do you call, there is a lot of literature on how you can do this, right. But the Smith chart is something that you need to be aware of, because you are going to see this a lot of times when you read RF papers or do RF work or use RF instruments, and okay. So, if you measure the reflection coefficient of, for instance, a capacitor, where do you think it will lie on the Smith chart? Pardon? Very good, right. So, basically the reactance of a capacitor is negative. So, you are going to be somewhere here, and that part corresponds to the lower half semicircle, right. If you measure an inductor, you are going to be, it's going to show up somewhere on the upper semicircle, right. The magnitude, as you can see, is always going to be 1. If you have an open circuit, you are going to be, or a short circuit, you are going to be, if you measure an open circuit, where are you going to be? This is the open circuit, right. And if you have a short circuit, where are you going to be? Well, all right. And if you have a fixed inductance but sweep frequency, where do you think, what will be the locus of the points on the Smith chart? You have fixed inductance, but you sweep frequency. At each frequency, you plot the reflection coefficient. Where are you going to be? Well, on this picture, you are going to be here, right. As you keep increasing frequency, the magnitude of the reactance will keep increasing, right. So, here you will basically, the inductor will basically be, will go along, you will see a curve on the upper semicircle, and likewise a capacitance, you will see a curve on the lower semicircle. Okay. So, so that is all that I wanted to say about the Smith chart. The next thing, I mean, a Smith chart is useful and is also historically important.